Have you ever wondered how we teach a computer to see? I mean, not just to recognize an image, but to truly understand what's inside it. Well, today we're going to dive into a pretty huge breakthrough from Facebook AI that completely changes the answer to that question. It's called DTER, which stands for Detection Transformer. And trust me, it's a whole new way of thinking. So let's break it down.
What we're looking at here is a task called object detection. It's one of the most fundamental challenges in computer vision. Getting an AI to not only say, hey, there are zebras in this picture, but to actually pinpoint each and every one with a super precise box. You know, this is the kind of tech that powers everything from self-driving cars to analyzing medical scans. It's a big deal. So, that brings us to the big question, right? How in the world do you go from just a pile of pixels to a meaningful, structured understanding of a whole scene? For years, the answer was, well, it was a mess. Incredibly complicated.
To really get why DETR is such a leap forward, we first have to talk about the old way of doing things. And let me tell you, it was a very, very messy pipeline with a ton of moving parts.
The best way to think about it is like trying to build one of those super intricate model ships in a bottle. Older methods had to rely on literally thousands of predefined guesses. They call them anchors. And then a whole series of steps to propose regions, classify them, refine the boxes. It just went on and on. Sure, it worked, but it was kind of a brute force approach, packed with hand-designed components and little rules of thumb that had to be tuned just right. And this slide really gets to the heart of the totally different philosophies. The old way was this cascade of messy subtasks. You make thousands of guesses with these anchors, and then you have to do this complex cleanup process at the end to throw out all the bad overlapping boxes. DOTR's approach? It's completely different. It just asks the right question one time. And this is where DETR comes in, introducing a much simpler and frankly more elegant way to think about the entire problem. The authors of the paper said it perfectly. They basically reframed the whole task. Instead of this clunky pipeline, they decided to view object detection as a direct set prediction problem. Okay, so what does that actually mean? It means you treat the AI model like an oracle. You just show it an image, and you ask one simple, end-to-end question: what is the complete set of objects in this picture? And the model's job is to directly spit out that final set of objects, the class, the bounding box, all at once. And that is the huge conceptual breakthrough here. So how on earth did they build a model that could answer such a complicated question in just one go? Well, it comes down to a really powerful combination of a few key ideas. So here's the high-level game plan. It starts with a standard convolutional neural network, a CNN. You can think of this as the eyes of the system. It's great at spotting raw patterns and features in the pixels. But the real magic, the secret sauce, happens in the second part, a transformer encoder-decoder. Yep, the same kind of architecture that totally revolutionized how we do natural language processing. And the pipeline itself is just beautifully simple. First, the CNN backbone acts as the eyes, creating this rich map of all the visual features. Second, that map gets fed into the transformer, which is basically the brain. And finally, some simple prediction heads, just little feed-forward networks, act as the mouth, turning the transformer's understanding into the final answer. Eyes, brain, mouth. That's it. Now, the transformer is the real star of the show here. It's the brain of the whole operation. Its self-attention mechanism lets it see the entire picture at once to understand relationships. The first part, the encoder, kind of looks at the whole scene and asks, what's going on here in general? Then the decoder uses that global context to ask really specific questions or object queries, like, okay, based on everything, is there a person right here? What about a car over there? So, how do you teach a model to give you just one perfect answer for each object? Well, it's done through this super clever training process using something called a bipartite matching loss. Think of it like a perfect matchmaking game. For every real object in the picture, the model has to find one and only one of its predictions to pair it with. This forces the model to learn not to make duplicate guesses from the very start, which completely gets rid of that whole messy cleanup step later. And what's so cool is we can actually see the encoder's brain at work. These heat maps show us its self-attention. Before it even tries to draw a box, it's already figuring out how to separate the different cows from each other and from the background. It's building that global context, understanding that these are all distinct things. Then, the decoder takes over. Once the encoder has figured out what's what, the decoder can really focus its attention. And we can see it here with the elephants. It's zeroing in on the extremities, the head, the legs, the tusks. It's using those key points to figure out the precise boundaries for the bounding box. It's just this beautiful division of labor between the two parts.
Okay, so the idea is elegant, the architecture is clever, but the million-dollar question is always this: does it actually work? I mean, does it perform as well as those old, complex methods that have been optimized for years?
And the results are, well, they're fascinating. If you look at the overall accuracy, that first AP column, it's a dead heat, 42.0 for both. Now, for a brand new architecture, that's incredible on its own. But the real story is in the breakdown. Check out the next column, for large objects. DETR absolutely blows the older model away, a score of 61.1 to 53.4. But there's a trade-off. As you can see in that last column, it struggles a bit more with small objects.
So what does this all tell us? It proves that this new, simple approach isn't just some academic curiosity. It is immediately competitive. And its superpower is obvious. That transformer brain, with its global view of the image, makes it a champion at understanding large objects. The trade-off with small objects is real, for sure, but it also points to a clear path for what to improve next. But this is where things get really mind-blowing. The model was trained on images that had, at most, maybe 13 giraffes. So the researchers tested it on this wild synthetic image that had 24 giraffes, way beyond anything it had ever been trained on. And the result? It found every single one. This just shows it's not memorizing patterns. It's learning a flexible, generalizable idea of what a giraffe actually is. So why does all this matter? I mean, why is this so important? Because this is more than just a new model with a good score. DETR's success really signals a huge, seismic shift in the whole field of computer vision. The real revolution here is simplification. By stripping away all those complicated, hand-designed components and human rules of thumb, DETR makes object detection a much more direct and, elegant deep learning problem. It just lets the model learn straight from the data, instead of relying on a bunch of human-engineered shortcuts. And here's where that simple, elegant design really pays off. Because the architecture is so clean, you can easily extend it to tackle even harder problems. With just a tiny tweak, DETR becomes a top performer in something called Panoptic segmentation, which is basically object detection on steroids. It's not just drawing boxes, it's coloring in every single pixel of the image and telling you if it's a sink, a counter, a floor, or a cabinet. Incredible. And that leaves us with this final, really exciting question. DETR proves that we can teach machines to understand what's in an image with a far more unified and elegant approach than we ever thought was possible. So if this is what happens when we simplify the problem, what new frontiers will open up next?